Okay, good afternoon, everybody. We're Wednesday the 22nd. We're gonna jump right back into our trig stuff. Section 7.5 is what we're gonna work on today, and I'm optimistic we'll be able to get into part of 7.6, so at least there won't be much left on Friday for us to do. We can just kind of focus on wrapping things up, getting ready for the quizzes and all that stuff. So today, as you see, hopefully on the screen, we have our analytical trig. We're doing more of that in chapter 7, and this is two formulas. Well, it's three formulas, but we have a handful of formulas, sum and difference formulas. So you'll find that this is not, it's really like it says. You're going to learn some formulas and we're just going to have to apply them. It's mostly going to be a lot of algebra. And then they're going to, of course, mix in the things that we've already been learning here. So when they say sum and difference formulas, you'll see exactly what I mean in a second, starting with this one. What it is when you have two separate angles inside of a trig function, like cosine. So for example, if I was to give you the cosine of, I'm trying to think of one that's easy to do. Let's make an easy one. 30 degrees plus 60 degrees. Now, we of course know that that's the same as cosine of 90 degrees. And we know that's a big zero, okay, from what we already had. However, there is a way to break this down where if you follow this first formula right here, this alpha and beta, that's these two angles I'm talking about right in here, cosine of alpha plus beta, basically they could be anything, any two numbers. And then as you see from the second formula, you can also subtract them. You can then break it down. It's kind of like a distribution. So obviously it's not going to be simply cosine alpha plus cosine beta, but it's this combination over here on the right is what all of this equals. So I'll kind of break this down how it works. You write it as cosine of the first times cosine of the second. So I'm going to take cosine of 30 degrees times cosine of 60 degrees. Then we're going to subtract the sine of each multiplied together. So we're going to subtract the sine of the first times the sine of the second. So that first step right there, that is a breakdown of just using the formula as it is. I'll consider this, it's no different than if you have the quadratic formula and you replace the A's, B's, and C's with numbers. We're replacing all of the alphas and betas, all of the angles into this second half of the formula. Okay? And sorry, Kayla, answering your question, I haven't been recording for an hour. I've been on for an hour. I just set up the video earlier, but I just started recording it a second ago here. So no worries on that. All right, any questions on these so far? Okay, so now we just have to go figure out the four trig functions. So again, I don't need to pull this up as much, but you guys know my little cheat sheet over here. We know these, right? Pull them back down. But the cosine of 30 degrees is a square root of 3 over 2. Cosine of 60 degrees is a half. Sine of 30 degrees is a half. Sine of 60 degrees is square root of 3 over 2. That gives me the square root of 3 over 4 minus the square root of 3 over 4. And we get our 0. Now, a lot of you are going to say, well, we already knew it was this up here. Why did I have to go through all this song and dance? You're right. We didn't need to do all that. I was just picking one that we already knew. But if you had to find something like, say, cosine of 75 degrees, this is not one of the angles that we've memorized. You know, down here in my, in my table, notice we go from 30, 45, 60, all the way up to 90. So we don't go every 15 degrees. We almost go every 15 degrees, but we don't have something like this. This formula would allow me to figure this out. I would rewrite it as cosine of 30 degrees plus 45 degrees. I then would go and get cosine of 30, cosine of 45, minus sine of 30, sine of 45, and then go break all these down. We get the root 3 over 2 times the root 2 over 2, minus the 1/2 times the root 2 over 2, and then clean this up, and you see we get root 6 over 2 minus root 2 over 2. You can't simplify that, as in you can't add these two roots any further. That right there, as weird as it might be, that is your exact answer. the precise answer. As you recall, sometimes they're going to say, give me an exact answer. Sometimes they're going to give me an estimated answer. And just look on our calculator right here. I'm in degree mode. I do this cosine of 75 degrees. I get this 0.2588. I'm just going to write that down over here. 2588. Now look at the answer that I just found. The root 6, figure that out. Root 6 minus root 2. That gives me a 1.035 on the top divided by 2. And, what did I get wrong here? Oh, sorry. Mistake on the algebra here. Go back. It's supposed to be 4s down here. We're multiplying these out. That's a 4. That's a 4. My answer is a 4. Almost had the precise answer. Just a little bit off. One more time. Try that out. Root 6 minus root 2 divided by 4. And you see we get the same answer, this 0.2588. So the decimal in the calculator is this, but the exact answer, and you can't clean it up anymore. Some of these, you can't simplify anymore, but this is the simplified form. This is our answer right here. And I say you can't clean it up. Yeah, you can factor it if you wanted to. If you wanted to take this and say, factor out a root 2 and get root 3 minus 1 over 4, that would have been fine, but it's not like it's any better. They're both going to be good. The point is, when they ask for exact answers, they don't want a decimal. They want something with roots and or fractions like you see here. Okay, questions on that one? Now I'll show you another one. Not that this is going to be the way to do it, but to show you there are multiple ways on this one. Remember again, the problem I just did was sine of 75 degrees. I could have gotten creative and said, well, how about if I do sine of 135 degrees minus 60 degrees? First, obviously, make sure that those two numbers subtract and they are 75, but you see the difference in this problem. I don't have 75 memorized. Remember, it's not in my list down here, my little 17 trig function results. There is no cosine or sine. And of course, you notice with the formula, you got to know sine and cosine. I don't have a 75, but when I break this down this way, I do know 135. I do know 60. So I should be able to get the answer the same way. This time I'm going to use that second formula over on the, on the page on the left there. So, show you what I'm talking about here. Now we're looking at, I'm sorry, and I haven't gotten to sine yet. I meant to say cosine. I'm still sticking with this first page here. The cosine of 75 degrees is what I'm trying to find. So, when I do a subtraction, notice the formula is pretty much the same. The difference is, when you're adding angles on a cosine, you have a subtraction of the results. When you're subtracting in cosine, you add the results. And notice it doesn't say it has to be in a certain quadrant. I could pick any two numbers that in this case subtract the 75 and this is going to work. So the formula is cosine of 135 degrees, cosine of 60 degrees, plus the sine of 135 degrees, the cosine of 60 degrees, just like that. Okay? Now, I like this because it kind of makes you start to think, oh, do I know what the answers are? We get a negative root 2 over 2, and we have a 1/2. Here we have a positive root 2 over 2, and the cosine of 60 is a root 3 over 2. Now, I'm hoping when you're doing your homework, you know these by heart, but here's what I'm going to do. I did these. I'm going to do a quick check. Now is the time. Don't write them down, but let's look in my table. Cosine of 135, there's my negative root 2 over 2. The cosine of 60, yes, there's my 1/2. The sine of 135, positive root 2 over 2. And the sine of 60, square root of 3 over 2. So we have our numbers good. Now, like I was saying earlier, it's just a little bit of algebra. We get this, we get this. And as you recall, oops, sorry, I did the same mistake again. These are supposed to be 4s down here. You're multiplying each of these fractions. And now, notice, we get this. Should be the same answer. And if you plug it into the calculator, you're going to get the exact same thing. It'll work. Okay? Any questions on these first couple? Yeah, cosine of 75, Jason, thank you. That was my mistake earlier. Anybody else seeing anything here for this? And as you notice, what's weird about these formulas, we're finding cosine, but the formula has both cosine and sine in it. You're finding cosine, it's got both of them here. In a second, we're going to do the same thing here. Yeah, that's right here. This is supposed to be, as I'm trying to explain it, I'm telling you the wrong thing. So not what I wrote. This is supposed to be sine of 60. Follow the formula. This answer was correct. I just wrote the wrong thing. So yes, in the cosine formula, it's a pair of cosines and a pair of sines, and then the number in between is the opposite of what you had originally. Whether it was a plus then becomes a minus, or a minus that becomes a plus. Okay, so now let's look at, where are we at here? Next formula. And again, this is just some examples you'll see here. I won't walk you through every single step, but I'll just kind of explain how they're doing it. They wanted to find the exact value of the cosine of 105. They started by picking 45 and 60. The key is pick two numbers you know, as in the angles. You know 45, you know 60, so go ahead and do those. Oh, sorry. And then fill in the formula. Cosine, cosine, and opposite sign in the opposite, plus minus in the middle, and then get those four results. And you're always going to get the four results, multiply them, and then combine like terms if you can, combine the fractions, and here's your answer on this one. Okay, now as you get to the radians, this will get a little bit more difficult in that it's pretty easy to eyeball it and say 45 plus 60 is 105. You can kind of play with those and get them to work. This 5 pi over 12 might be a little bit more difficult. So here, and you might just have to play with it a little bit. Cosine of 5 pi over 12. Well, I can make it 2 pi over 12 and 3 pi over 12. Those don't look familiar, but when I simplify them, now I have a pi over 6 and a pi over 4. And that should trigger your memory and say, yep, I got a pi over 4. I know those. I got the pi over 6. I know those, the 30 and the 45 degrees. So yeah, I should be good with both of those as my result, as my new options here. So same thing. We have an addition going to this one on the right. That means it's cosine of the first times cosine of the second. Remember, these are multiplied. Opposite here, so it's a minus since that was a plus, sine times sine. And we get our four results, multiply them together. And you're going to see a commonality. You're going to see lots of these root 6s in these types of problems because you're multiplying root 3s and root 2s. Then you're going to see some root 2s and root 3s, but those are the roots you're going to get, and it all is different for each number. Okay? So now we have some identities, and we had these earlier. If you recall, we talked about it might have been if you add pi over 2 to the end or subtract pi over 2, you had the same thing over there. But this is now going to prove these identities. Because notice what happens is, even though it's a theta, it's still two angles in the middle. So it's two angles with a subtraction. This is going to go back to this formula right here, this second one, formula theorem number 2. If I have a cosine of an alpha minus a beta, I can figure that out. So this is what it is. This is my alpha right there. That's my beta, even though it's already got a theta in there. But we can go figure those out. And essentially, they didn't break it down, but let me just show you real fast. If you have a cosine of pi over 2 minus theta, remember the formula that we just did. It's the cosine of pi over 2 times the cosine of theta. Plus, because it's the opposite sign, the sine of pi over 2 and the sine of theta. Well, I know the cosine of pi over 2 is 0. I know the sine of pi over 2 is 1. So do you see how this whole thing simplifies? That's gone. And that's how we know it equals sine of theta. And you can do the same thing on the next one. It'll work exactly the same. So a lot of these, you're going to see these theorems or identities, they form from other theorems and identities. You just keep building. Like the example I did Monday, how I had 5, 6 different things and they're all equal. Not saying they're all good, but they're all equal forms. That's what identities are. It's just other ways to write the same formula, to write two things that are identical. Okay, So now we have the same formula as the sum and difference for a sine function. So if you have sine of two angles adding or sine of two angles subtracting, here are the results, but unfortunately they're completely different. Remember for cosine, it was cosine times cosine, and then plus or minus sine times sine. Here it's a mix of the two. So it's sine of the first, cosine of the second, and you keep that plus or minus identical. So that's the one good thing. And then it's cosine of the first, sine of the second. And these are ones where you literally have to just sit down and memorize them or have a sheet of these nearby. And that's how you can apply these concepts, you know, how you can memorize them. And trust me, you copy these enough time when you're doing your work, you're going to start to figure them out. You're going to start to see them. Okay. So the first example they're going to give you is this sine of pi over 12. And I'm going to work it out over here. Now, if you want, don't be afraid. You might be able to do this in your head. You might not be able to. But remember the process of converting into degrees? It's 180 divided by 12. This is a 15-degree angle. So I only do that to show you that, well, I only know from my sheet over here, I only know 30, 45, 60. There's no way I can add any two numbers to get a 15. I'm going to have to subtract something. So I got to think, what can I subtract to get a 15? What can I subtract to get a pi over 12? Well, let's make it as easy as possible. How about we do 45 degrees minus the 30 degrees? Okay, so 45 degrees minus 30 degrees. That's going to give me my 15. So that's where I get the pi over 4 minus the pi over 6. That's how I got those two results. Okay, so now I'll do something different in this example just to get you in a good habit and to help you to know these better. I'm going to write this formula out. The alpha minus beta. So remember how it is. It's sine of the first, cosine of the second. Keep that plus or minus identical as opposed to the cosine where we use the opposite one. And then you do cosine, you flip them. Cosine of the first, sine of the second. Okay, just like the formula there. With me so far? Any questions? I'm using, of course, this formula or theorem number 5 right down here. Identical to what I just wrote. And the reason I do this is, especially for these, it makes it easier to pop things in. So just to identify, remember that right there is the alpha. That right there is the beta that I was talking about. So when I plug these in, anytime I see alpha, I'm putting the pi over 4. So I get sine of pi over 4. And then I have cosine of pi over 6 minus cosine of pi over 4 and sine times sine of pi over 6. All right, now at this point, you know these answers, but take your time and get them right. And it's always going to be 4 different things. The first 2 multiplying together, and then the second 2 multiplying together. Stop me if you have any questions, anybody here. I'll keep checking the chat, but if you don't see me respond in the first few seconds, don't be afraid to unmute and yell out to me so I can address your question, because these problems are going to get larger, and I don't want you to be stuck on step 1 when I'm on step number 9 here. And like I said, a lot of these are going to look the same. Here's my root 6 minus root 2 over common denominator 4. There is my exact answer. Okay, so do a calculator check. And that's a nice thing. Even though they may say, give me an exact answer, you know you can do this right here. Okay, let's do the sine of pi over 12. Now remember how to do this if you're not sure. I can do the sine of 15 degrees. That's what we already figured out it was. And I get this 0.2588. Seem familiar? I'll tell you why in a second. Okay, we did that earlier. But I can also plug in radians, pi divided by 12, and then take the sine of that, and what do you know? 0.2588. I can do these roots over here. Root 6 minus root 2 equals divided by 4, and no surprise, 0.2588. Okay, so if you're ever asked on, especially on a quiz, hey, I need the exact answers. Whether this is in class or an online course that you're taking it in, this is what you have to put in the box. But as you go through this whole process, if you're not sure, you can easily whip out your calculator and just see, does the decimal I get equal the decimal in this box? If it does, and that sort of confirms you had the correct answer right here. Okay? Questions on this example that we had here? Then I'll pull up the slide here and you'll see it should be exactly the same, I hope. So kind of go through the process, same exact thing I had. They went with these two numbers. And remember, these are not the only two ways to get the pi over 12, to get the 15 degrees. I could have taken the sine of 135 degrees minus the sine of 120 degrees. It would have worked. I could have taken 330 minus 315. There's a number of ways to subtract and or add where you can get the desired result here. So you have to work backwards a little bit, but once you get to this part where there's two things, then you just plug them in. And remember, these two, you multiply, and then add or subtract the results. Okay, so another one now, this is where you can kind of look very smart. If you're given a problem that looks like this, where it is sine, that right there, they're asking what's the exact value of that. If you can recognize the formula, you can work backwards on that formula. So remember these two formulas that we had a second ago. Okay, remember these? And then you had the cosines. Recognize which one you have. I have a mix, a sine and a cosine, a sine and a cosine. That's this formula right here. Remember the cosine ones? It was cosine, cosine, sine, sine. So then we'll deal with the plus minus later, but we have this, which tells me, okay, this is definitely going to be a sine of something. And I've got an alpha and a beta. This looks like my alpha because it's here and here. This is my beta because it's here and here. And then remember the rule. Because that's positive, in a sine formula, it's the same thing. It's going to be also positive. So my answer to this problem is, let's just take that 75 degrees, add it to the 15 degrees. Sorry if that's messy. And then where do you go from here? You don't go back to the formula. You can say, well, this is the sine of 90 degrees because I add them up, and I know the sine of 90 degrees is 1. I can save the trouble of going through all this stuff by going backwards on the formula. So a lot of these theorems, they are not just one direction. You can go here or you can go backwards there. It just depends on what you were given, what you were asked to find in any of these problems. Okay, any concerns, any questions about any of this stuff here? Okay, so now let's look at another one. Okay, we're going to go next level here. They tell us the sine of alpha equals, make sure I got the right first page here. Sine of alpha equals 1 over the square root of 2. Then they tell you the alpha is between pi over 2 and pi degrees, or radians. Then they give us sine of beta is negative 1/3, and that's between pi and negative 3 pi over 2. And they want us to find all the following of these. There's a lot of stuff going on here, so we need to figure out where we are. So I'm going to start with drawing a little bit of a table or a graph. You don't have to draw this, but this just might give you an idea. So keep in mind, there are two things we're dealing with. There's an alpha and a beta, and we don't know either of them. We know a little bit. So starting off, we know the alpha is between pi over 2 and pi. So my alpha is somewhere in here. Okay, between pi over 2 and pi. The beta is between pi and 3 pi over 2. So my beta angle is somewhere over here. There's my alpha and there's my beta. Now what they're asking for is they want to know what's the cosine of alpha. They want to know what's the cosine of beta, the cosine of the pair, the sine of the pair. We need to try to figure all that out just from this picture right here, just from all of this. So let me start with just the alpha. Okay, remember how we did this before? We know the sine of alpha equals 1 over the square root of 2. And again, these are like my favorite problems because they really test your knowledge of everything. So we already identified it's in the second quadrant because of this statement. Okay, so now we've got that. I've built a triangle. I have no idea where it is. I mean, it could be 91 degrees. It could be 179 degrees. It could be 135 degrees. I don't know. I just know it's somewhere in there. But now, based on this on the top right, and I remember my formula for sine, which is y over r. Okay, I know I have a 1 and I have a square root of 2. And I need to go find this x. We're only talking again about the alpha right now. That's all I'm looking at. That's all I'm dealing with. Okay, so now I can go figure out and say, where are we? The sine of, sorry, Pythagorean Theorem is what I meant to do first. So 1 squared plus x squared equals root 2 squared. That's x squared equals 1. 2 squared of 2 squared is 2, minus the 1, we get a 1. So x equals plus or minus 1. Because we're in the second quadrant, I can say I know this is negative 1. And now at this point, I can find the sine, the cosine, the tangent, the secant, anything of angle alpha. So for here, I know the cosine of alpha is going to be negative 1 over the square root of 2. Any questions on that first piece that I did? That was kind of I don't want to say a review, but that's a problem that we had recently. You're given a little bit of, you're given one trig function, and then you can build the triangle, and then you can build the full triangle so you can get every one of the other 5 trig functions as needed. Okay, so now, notice I still don't know what alpha was, but I do know the cosine of alpha. I can get the tangent of alpha. I can get anything of alpha if I need it. Okay, so now let's go down here and let's look at the beta. We already said the beta was going to be over here. So let's build my right triangle. And just keep in mind, you guys, when you build that right triangle, it's always touching the x-axis. It's either going up or down. You never build a triangle over here. Okay, it never goes right and left like that. The 90-degree angle should always be touching the x-axis. So now they told us that the sine of, and this is beta, by the way, the sine of beta equals negative 1/3. So that again is my y over r. Who is negative? Well, I already told you that the r always has to be positive. Therefore, the sign has to be the negative. The negative's got to go with one of those, the 1 or the 3. It's got to go with the top, the 1. And of course, that fits our picture. Excuse me. That fits our picture because it is in the third quadrant, so it is going down, hence the negative number. So I do the Pythagorean one more time. X squared plus negative 1 squared equals 3 squared. I get x squared equals 9 minus 1, so it's that. And hopefully you can see this on the bottom. It's plus or minus the root 8, or 2 square root of 2. Since we're in the third quadrant, this is going to be a negative root 2 over 2. But at least that opens a door, because now I can go figure out that the cosine of beta is negative root 2 root 2 all over 3. And there's my second answer. So now we figure out the other pieces. Well, the cosine of alpha plus beta, the only way to get this, because again, notice I know everything about alpha's triangle, I know everything about beta's triangle, but I still don't know what alpha and beta actually are. I still don't know how many degrees or radians those are, but we don't need to. We just have to know the trig functions. Well, now this alpha plus beta is going to be somewhere, I'm thinking in the back in the first quadrant, and I need to find all those results, but I have formulas now to do this. Now that we can add alpha plus beta inside there, I know it's going to be cosine alpha, cosine beta, minus sine of alpha, sine of beta. The second theorem, or the first theorem that I gave you guys today. And a lot of people will say, well, why couldn't we have done this first? Well, look at what they gave us. They gave us sine of alpha, they gave us sine of beta. We would have been able to get this and this, but we would not have been able to get these two. That's why we had to do these parts first. This gives us the other pieces involved in this process, this problem. So now I can get that. I see we have a negative 1/2. We have a negative 2 root 2 over 3 minus from the formula. And we have 1 over the square root of 2. And we have a negative 1/3. So when all's said and done, I can make these 2's cancel and the negatives cancel. I get a root 2 over 3 minus, which becomes a positive. Looks like 1 over 3 root 2. Erase a little bit up top just to finish off this problem so you can make sure we see how we got this answer. Then I'll show you the other one in the PowerPoint slide. So I have a root 2 over 3 plus a 1 over 3 root 2. And generally you want to simplify. If possible, that means combining fractions. So I have a 3 root 2 over here. I just put a root 2 here and here. And now I have a common denominator of 3 root 2. That gives me a 2 plus 1. That gives me a 3 over 3 root 2. And you see how after all that, we end up with a nice, tidy little answer right there for this. All based on the things they gave us in the beginning. Okay, before I erase this, any questions on anything for the first 3 parts? I didn't do part D yet. Excuse me. Okay, so let's look at what we get in the rest of this problem here. Now, they went to the unit circle. I'm doing that right triangle approach. Remember, you can do either or. As long as you get the y and the r, you get the x, y, and the r, you get all 3 values, then you're okay. So you see we get this negative 2 root 2. I hope that's what I said we had earlier. And then they do the same thing. Yeah, different approach, the alternate approach, the Pythagorean identity. I know a lot of students don't care for this because you get too much going on, but it's just showing that it will work out. Okay, and then we find the other value for beta, the cosine of that beta, and then we plug everything in here. And did I miss something here? I should not have erased it. I'm sorry. Let's just look at what we have here. We have cosine of alpha is this negative root 2 over 2. The cosine of beta comes up to be negative 2 root 2 over 3. And then we plug those in. Yeah, that seemed different than what I got earlier. Apologies on that one if I jumped the gun. So read this is better here, just in case. If those of you watching the video later don't need to rewind, just look at what we have right here. And combine everything inside that square root. And so you see where this came from, this first part. The negatives canceled. We have a 6. 2 root 2 times 2 root 2. The root 2's become a 2. That's why there's a 4 right here. And of course, here they cancel off and you get a root 2. And so there's your answer right there. And like I said, before I erase it, what I should have done is gone to my calculator again. I can easily go and plug these in just to see if they work out. We didn't have an original number, so that might not have been as good here, but it's just another choice to see if they're equivalent. Now for the sine of alpha plus beta, again on that one, we're using the different formula. So here's the cosine formula. Here's the sine formula. Sine alpha cosine beta plus cosine alpha sine beta. And again, get your 4 values. Since you had the triangles built, you can get those 4. And then multiply, and simplify. And the step they didn't show in the middle was what happened when you cleaned all these up, what you get. But here's our results. Okay. And I think, yeah, everything should be good. Yeah, this is the 4. And they went backwards. If you're looking at this later, there's a negative times a positive. It's a negative. The root 2's become a 2. The 2 times 2 is a 4. That's how they got the negative 4 on the back end here. And then in the front, this negative, and we have a root 2 on top. That's where they got this from. So that's all that happened on that one. Okay. So let's look at another one. Now we're back to what we did the last 2 days ago, establishing an identity. So we have this cosine of alpha minus beta all over sine of alpha sine of beta. That is supposedly going to equal cotangent alpha cotangent beta plus 1. Okay, so show you this here. Go step by step so you're not getting overwhelmed on these. Now, what they're doing, and I would like this too, is when I got all this, remember our rule. Let's pick one side and work with that one. I don't like to have this complicated parenthesis in there, so that's usually the side that I want to attack, since I know there is a formula that'll take care of this alpha minus beta stuff. So this left fraction is what they dealt with. They left the denominator still as sine alpha sine beta. On the top, where it was cosine alpha minus cosine beta, this is literally a rewrite of that formula from one of the first slides of today. Cosine alpha cosine beta plus sine alpha sine beta. Change this, the minus to a plus here. Okay, now always keep in mind this right side, this cotangent alpha, cotangent beta plus 1. Now the tricky part is you have to be careful when things cancel. Whereas before, if you had a sine over a sine, it became a 1, that was because they were both thetas. When you have an alpha and a beta here, you better make sure the sine will cancel with sine only if they're both alphas or both betas. So don't jump the gun when you cancel things off. Okay, another thing to point out. There are 3 terms in this problem. There's 2 terms on the top, and there's 1 term on the bottom. Clear that up. Remember what we said last time? These things multiplying, that's 1 term. Here's a plus. Now there's another term. Now there's another term. The reason I say this is, if you want to cancel a sine of alpha, it better come from all 3 of them. Well, I have a sine of alpha here. I have a sine of alpha here. But notice no sine of alpha here. That means you cannot cancel them. Same thing with the sine of beta. As long as all 3 terms have it, cancel away. But if 1 term is missing it, you got to leave them all. Okay? So now what I will do is see if there's a way to clean this up factor, whatever it is. But what's going to happen next is I'll give you another example. You guys remember what happens when you add up 3/7 plus 2/7? Because you had a common denominator, you can combine them and get this 5/7. It's this middle part that I want you to see, that I want you to focus on, okay? When you have any 2 fractions, if you have 1 fraction with multiple terms on top, with 1 term on the bottom, it's just like this right here. And we're going to actually go backwards. You can take that and split that into 2 fractions all over the same thing. So that's what's going to happen on our next step here. So let me clean some of this up a little bit. Okay. So this is what happened. Notice you had 1 term, a sine alpha, sine beta. That's considered 1 term. So don't wonder why am I calling that 1 term? It's not, it's because they're multiplying together. 2 terms adding or subtracting is what you have, but that's just 1 term down there. So what we did was we took this and put it over the denominator to get that fraction. We took this and put it over the denominator to get this fraction. That's how we ended up with these 2 pieces. Now, almost always we've been taking fractions and combining them. Why in the world would we be splitting them up now? You'll see why in a second. It's because now you can do some cancellations. See over here? I can cancel these and I can get this whole thing to become the 1, like that. And then over here, this cosine alpha over sine alpha, that becomes a cotangent alpha. This cosine beta over that sine beta becomes a cotangent beta. And now we have made this left side equal to the right side. So this idea of establishing identities, we've already been doing it. We're just going to add in a new level, a new flavor, which is we now have these sum and difference formulas. Just look at it though as if you see them in an identity, that should be the first thing you attack. Go rewrite that with your formula like this, and then go and see what simplifies, what cancels, what combines, and try to work it to make it become that right there. Okay, stop me if anything's unclear. Any questions from any of you here today? Okay, let's look at the next slide here. Now, the tangent alpha plus beta, tangent of alpha minus beta, it's as important as the other ones, but it really is not as common. You're not going to see this nearly as much as a sine alpha plus beta, cosine alpha plus beta. So the first 4 I gave you, you're going to see a lot. These 2, you're going to see them once in a while. Okay? So here's what I would tell you. Don't worry about memorizing these. These come up so rarely that you just know they exist and be able to look them up. And I'm talking in Calc 1, Calc 2. You'll see them rarely, but you will see them once in a while. So no big deal. Just pull them up and refer back to them. So here we're going to establish the identity. Now, as I do this, I'm going to go back and forth to kind of peek at this sheet that I just told you about. Advice should be is have all these formulas on a single piece of paper, or a single file like I have with the sines and cosines, all those angles. Have this nearby. Just know that it's out there and you can pull it up. Refer to that very easily when needed, like I'm going to do here. So we have the tangent of the tangent of theta plus pi. So it's not as simple as the sine and cosine when you're adding them, but there is a formula. Here's that formula again. Okay, so let me go back. The formula is that top one. Notice it's the tangent of alpha plus the tangent of beta. Then on the bottom, it's the 1 minus, and you multiply the two. That's where this formula does get confusing. Because on the top, you add the tangents. On the bottom, you multiply the tangents. And the only thing that changes is the pluses and minuses are kind of all over the place. The top plus minus matches what was in the parentheses originally. The bottom one is opposite what was in the parentheses. So that being said, here's what we have. We take, remember the top, tangent of alpha, tangent of the first, plus tangent of the second. There's the 1, there's the minus, and then we multiply the 2, just like that. Now this is like one that I showed a couple minutes ago where you don't know what the theta is, but you do know these two. And that's the whole point of this identity. Okay, so we know the tangent of pi is 0. Think about that for a second if you're not sure. Remember, tangent is sine over cosine, and the sine of pi is 0. So you essentially have a 0 over negative 1, which is a 0. So the tangent of theta plus 0 over 1 minus the tangent of theta times 0. So that's going to cancel off. And we get just the tangent of theta over 1, which is just tangent of theta. It's a very quick process. It's really just a matter of were you able to plug in the identity, the new formula that I just gave you here. Okay, here it's the same kind of thing. All right, we're going to plug these in. Same, little different here. Let me go back. So 2 ways you could have done this. This is one way where instead of me using this formula right here, okay, I could have easily used this formula to get the answer, to split it up, to split the alpha and the beta. Instead, what they opted to do was, let's rewrite tangent as sine over cosine. So that's what this was. And notice it doesn't matter what's in here. If it's the tangent of alpha, it's sine alpha over cosine alpha. If it's the tangent of 194 degrees, it's the sine of 194 over the cosine of 194. Okay? If it's the tangent of this mess, it's the sine of that over the cosine of that. It is irrelevant what's inside the parenthesis. What matters when you use this quotient identity, this tangent equals sine over cosine, all that matters is make sure it's an identical angle. Whatever you started with is in each of the sine and the cosines, and that's what we have done here. Okay, so now look what's going on. I won't say it, but I'll let you figure it out. You see what they did here. Look at the previous step. Look at the step we have right now. So if you notice correctly, that's all that happened here. We took this top and we used the sine of alpha plus beta formula, the sum, which remember is sine of the first, cosine of the second, plus cosine of the first, sine of the second. For here, we use the cosine formula, which is cosine of both, opposite sine of both. And now, let's see if we can figure things out. What's nice about this is don't go any further without now removing all the ones that have pi over 2, because those are angles that we know. We know the cosine of pi over 2, it's a 0. We know the sine of pi over 2, it's a 1. Cosine of pi over 2 down here is a 0. Sine of pi over 2 is a 1. So that was the replacements on this step. And as I mentioned on Monday, I'd recommend, I won't make you do this, but I'll recommend when you're doing this, you should have this right down here. So you're working downward. This step would be right here. This step would move down, just like it went right here. See how it's so easy to see? It flows right downward. Instead of going left to right, it's so much easier in my mind to go straight up and down because you can literally see what has changed. Like when I'm looking at this and I'm trying to check my work, I can see, well, this stayed the same. This whole thing became the 0. This whole thing became the 1, and it's easy to follow the breadcrumbs. You know, you can see exactly what went to where. Okay, so we're almost done. We're not quite finished yet. Now we get rid of the ones that were zeros, that one and that one. And you see we get cosine over negative sine, which then reduces back down to negative cotangent. Okay, so it's a nice, elegant way to show the answer. It's not always easy to come up with it on your own. And that's the tough part. You know, following what I'm doing here, I know is a lot easier, and many times you can follow it. Then I give you the problem and you have no idea where to start. But just think of all your options. That's why we do so many of these is every time I see tangent, I can write it as sine over cosine. Anytime I see a tangent with two angles inside like this, I could split it up with our newly learned formula. Same with the sine of two angles and the cosine of two angles. You can always split them up and then see where, like I said, where the chips fall. A lot of times on these identities, whether it was these or the ones from 7.4, you just have to have a little bit of a leap of faith where it's like, I'm not sure where it's going to go, but I'm going to step out here. I'm kind of falling blindly and taking a step, not knowing what's on the ground in front of me, but just take where you think is the best option. And then all of a sudden, things will start to appear. Things will get better. All right, now we get to some other ones that I like that sort of combine a couple more elements that we've recently learned. We want to know the exact value of the sine of the inverse cosine of a half plus the inverse sine of 3/5. Okay, so let's do a quick refresher. Remember, inverse trig functions, those are angles. So in the past, if I was to see this, I would call that thing theta. I would go build a triangle and I'd figure out what we have. Okay, now the problem is we have two different things going on here. So what we're going to do is we're going to call this one alpha, and this inverse trig function, I don't know what it is. I cannot assume they're the same. I'm going to always assume they're different. So I'm going to call that one beta, and I'll see what we get. So that's the first step. Alpha is the inverse cosine of a half. Beta is the inverse sine of 3/5. And in each case, they're going to go figure some things out. Now, they went through this part. We don't know this yet. So what I'm going to do is I'm going to go right to the triangle approach that I had from before. So let me just recopy this problem, if you don't mind. We're looking for the sine of the inverse cosine of a half plus the inverse sine of 3/5. Now I want to point out that these are different angles. We always assume they're different angles. Whenever you see an inverse trig function, it represents an angle. If you see another one in the same problem, you must assume it's representing its own angle. Even if these were, say, both inverse cosines, that means nothing. Even if one was inverse sine and one was inverse cosine, but they had the same number inside, they're going to be different angles, okay? So always assume they're different when you're figuring this out. So we have the alpha, as you recall, is the inverse cosine of a half. This means cosine of alpha is 1/2. And that's what I'm going to build the triangle on. Okay? So, going back to the original, I'm just going to go back to that real quick. They didn't really tell you anything about it. Okay? It's not very clear about as in where the angles are. So you have to just kind of figure them out. But this is where we go and think. Remember? Inverse cosines are always going to be in the first or second quadrant. So I either have it here or I have it here. That's the only place an inverse cosine could be. It's got to be one of those two. Well, let's see. Since it's a positive cosine, I know it must be in this spot right here. This has to be my alpha. This one would give me a negative alpha, so that's not going to be where the alpha is. It's got to be in that first quadrant. Okay? So now, cosine is x over r, so there's my 1 and my 2 from this. We do the Pythagorean Theorem. We get y equals plus or minus root 3. 4 minus 1, 3. Square root that, we get a root 3. And because it's in the first quadrant, I go with the positive version. Okay, so now remember, by this triangle, I now know cosine, sine, tangent, secant, cosecant, and cotangent of alpha. I know everything there is to know about alpha because I have a triangle with all three sides filled in. Okay, so before I do the second part, any questions where I am at right here? Okay, now let's look at the other part. Beta equals the inverse sine of 3/5. So the sine of beta equals 3/5. Inverse sine has got to be in the first or the fourth quadrant. So it's either here or it's either here. You can tell by if that's plus or minus. If it's positive, we're always in the first quadrant. If it's negative, then it's either going to be in it's going to be in the other quadrant. This is positive, so this is going to be where my my beta is, not that one on the bottom. Okay, so just like I did a minute ago, exactly like the triangle on the left. I see the 3/5. Remember, sine is y over r. So there's my 3, there's my 5. When I do my Pythagorean theorem, 3 squared plus x squared equals 5 squared. X squared equals 25 minus 16, 25 minus 9, that's 16. And I know that's getting messy, I'm sorry. There's my 4. And if you forgot, remember there are 3, 4, 5 right triangles. So if I have a triangle that has 3 and 5, I know it has to be a 4 if it's a right triangle. Okay, so once again, I know everything there is to know about the beta triangle or the beta angle. Okay, so real quick, I'm going to go back, or not going to go back. The question now is asking, what is the sine of this plus this? So as you recall, that's an angle, that's an angle. They're essentially asking for what's the sine of alpha plus beta. Okay, that's all that's being asked here. They didn't ask to find the alpha. They didn't ask what to find the beta. They're just talking about something with the alpha and beta. In fact, the problem doesn't even say alpha and beta. They're just talking about an angle right here, such that the inverse cosine is 1/2. So what's the angle? That's what whatever goes in there is my alpha, there's my beta. So I now apply our new formula, which as you recall is sine of alpha cosine of beta plus cosine of alpha sine of beta. Now, I again wish I did have a larger screen, so I'm sorry if it starts to get a little messy, but we'll fill them in and then we can start erasing some stuff here. Okay, so I'm going to move this up to the very top, by the way. So the sine of alpha, going to this triangle right here, that's going to be the square root of 3 over 2. Looking at this triangle right down here, the sine of it is y over r, square root of 3 over 2. The cosine of beta, now we go to the beta triangle, the cosine of beta is 4 over 5. And then we have to have a positive in between. Now we look at the cosine of alpha. Well, guess what? We were already given the cosine of alpha. It's 1/2. Or look at the triangle. You can see the 1/2 right there. Last is the sine of beta. Again, we were already given the sine of beta. Or look at the triangle. You get the 3/5. Okay? So now, let me pull the slide down real quick. Just to give us some room to work here. And I'll pull that back up in a second. So now we don't really have any more use for the triangles. We've done all this. And now we have our 4 pieces. Sine alpha, cosine beta, cosine alpha, sine beta, and we know what those values are. Our last job is let's just figure out what the final answer is going to be. 2 squared of 3 over 5 plus 3 over 10, I think I have. All right, and I actually probably should have gone back to that 4/10. Instead of canceling off, I'll just go back to the 4/10. Just to make the common denominator is where I'm going on this one. So now we have 4 squared of 3 plus 3 all over 10. And there's our exact value. Okay, it's a long process in the fact that there's a lot of steps, but you just have to go piece by piece and figure it out. All right, questions on any part of this one here? So, is there a problem? I'm trying not to erase what I had just to show that we got the same thing, but there it is down there, right? 4 squared of 3 over 10. Oh, sorry. Yep, so we at least had the right answer. Now I can erase and just let you look at the slides here. Okay, so they, again, had to break it down, but in each case, you have to get the triangle. You use this first part to get everything there is to know about the alpha. Here, you use that to get everything you need to know about the beta. And then, of course, our formula involves both sine and cosine of the alpha and the beta. Okay? And yep, so I think you got that. Your 4/5, yeah. Other questions about this one? Okay, so a couple more things here. And it starts to get, this is one of these, I'll tell you, it's like the next level up there, but it's doable to us. Okay? They want us to write the sine of the inverse sine of u plus the inverse cosine of v as an algebraic expression containing u and v. So if you compare to the problem we just had a second ago, we had a trig function of two inverse trig functions, but we had numbers here. These numbers allowed us to make the triangles to get definite values, hence why we have these four numbers and we got one grand number at the end. Here, instead of a half and 3/5, all they tell you is u and v. They don't tell us anything. Okay, so the process is the same way. I'll go with the triangle approach again, just because you're more than welcome to use the method they use. I just like to be a little more visual, so I kind of show you what I'm talking about. Like before, I'm going to call that first trig function, inverse trig function, the alpha. That one's going to be the beta. So ultimately what they're looking for is what's the sine of alpha plus beta. Okay? So of the alpha equals inverse sine of v. And again, I know this is awkward because you have so many letters here, you don't know what to go with, but kind of follow the same path. This means the sine of alpha equals v. If that was a number, you would have done the same thing. So when I try to build my triangle, I'll go a step further and say it's basically the same as v over 1. So when I make this alpha triangle, there's the v, there's the 1 right there. Then I have to try to get this value, and I want to get that in terms of in terms of v, so I do my Pythagorean theorem, and I get x squared equals 1 minus v squared, x equals the square root of 1 minus v squared. It's not pretty, but the goal is everything in my problem, my answer should be only u's and v's. Okay, so as not pretty as this is, if I was told to go get the sine of alpha or the cosine of alpha, I can get it by simply looking at this triangle and using v or 1 or that square root of 1 minus v squared. Okay, but that gives me everything. And on the other hand, for the cosine, the beta equals inverse cosine of v. And I'm sorry, I wrote v when I should have done u right here. Apologies, I can fix that very quickly. Sorry, the sine was supposed to be u's. So that's a u, that's a u, that's a u over 1. Means that's a u over 1. And when I do the Pythagorean theorem, it's the square root of 1 minus u squared. So that's all it was. Easy fix. For the cosine of v, that means the cosine of beta equals v over 1. And same exact thing. And even though this is not easy to visualize, it's very good practice for you all to kind of know where everything is assigned, where you get everything. And then this little side right here is going to be the square root of 1 minus v squared. Okay? So now again, I know how to find everything for sine and cosine. Formula. Let's do this. Let's move it up to the very top. I want to get the sine of alpha plus beta, right? So once again, like every problem in this section, you're going to apply the newly learned formula. And now I replace every trig function with its equivalent value of hopefully one of those two triangles on the right side. Okay, so look, when you see sine of alpha, we go to the alpha triangle, this top one right here. The sine of it is u over 1, or just plain u. Cosine of beta, we go to the beta triangle, and cosine of beta is v over 1. Okay, so far it's pretty easy. Now it gets not as fun. The cosine of alpha, back to here, is the square root of 1 minus u squared over 1. The sine of beta is the square root of 1 minus v squared all over 1. So what they want is, this is mirroring what we did a second ago in the last problem. They just want you to come up with some kind of a formula, an answer that has only u's and v's in it. And that's what I have right here. Now, as much as you want to cancel those square roots off, you can't because the insides are not the same. So you just shove the two insides together, and this is pretty much the end, is where I would stop. You could FOIL that thing out, but you're really not going to get anywhere good. You're not going to get any kind of a better answer. So leave it right where it is. That's as far as you can go. And there's the answer they're talking about. Okay, so you're not going to get many, if any, like this on the homework. It's a higher level problem, next level. I like to still, though, try to push you guys a little bit so that you can get comfortable. But here's the answer that we just got. Okay, it's good just so, if anything, if you can just follow the procedure, it makes you that much better so that when you had one of these problems, you'll be looking at it and say, wow, this is easy because I got numbers, whereas this one right here was difficult because of the letters. I've pushed myself, so this is hopefully a much better problem to understand and to complete. Okay, so our last one here, I'll do one more problem like this. We have the sine plus cosine equals 1, and now we have to solve. So remember the answer to solve. Back to algebra, we're looking for what value for theta makes this equation true. And they only want answers between 0 and 2 pi. So a couple of things here. You can square, and I like this process the best, quite honestly. You square both sides and square, you should have squared this one, but the square of 1 is just 1. And when you square this, remember, you have to FOIL it out. It's a parenthesis sine plus cosine times another parenthesis sine plus cosine. And that gives you sine square plus 2 sine cosine plus cosine square. And then remember, the sine square plus cosine square is 1. That's why they're gone. And then you subtract the 1 over here, and that's why it cancels and it becomes a 0. Then we divide by 2, and basically we have sine times cosine equals 0. And we're solving for theta now in this case. What theta is, hopefully there's more than one. Which ones work? That's the test. So where is my little cheat sheet over here, just so we can quickly look at it. I'm looking for a value so that when I multiply sine and cosine, there is 0. The only way this works is if one of them is 0 and the other one is 0. So it works here at 0 because sine is there. It works when cosine is 0, so pi over 2, and pi, and 3 pi over 2, and 2 pi. Actually, you can't use 2 pi because they don't want it equals to. It's got to be strictly less than. So I'll get those first 4 answers, 0, pi, pi over 2, and 3 pi over 2. Those are our solutions. And that's probably your easiest way to do this. Now, if you do download this PowerPoint, you're going to see this is them testing them out. And, I'm sorry. Go back. I forgot one important thing. Where was it? Okay. Original problem. Remember this? When we squared both sides? You've done this before back when you had a problem, say, like this. if I asked you to solve the square root, the square root of x equals, say, 3, your process is you square both sides, and you get x equals 9, and we're done. No big deal. Okay, the problem was sometimes, even though you're allowed to do this, when you square, you produce answers that aren't actually legitimate, that aren't actually good. And you'll see in the next slide, they call them the extraneous answers. They're kind of like false answers that appear, false positives, whatever you want to call it. So the solution is, anytime you square a problem on both sides, even though you're allowed to do it, you just have to check your answers in the end to make sure it was good. So that's what the second part of the problem is doing here. We got the answers of 0, pi, pi over 2, and 3 pi over 2. Okay, so remember that over here? We have to check all 4 of these answers. So that's what they did right here. Plug in the 0 to the original problem. You get 0 plus 1 is 0, and that was the solution. Remember the original equation? They had to equal 1. So that's a solution. That confirms that 0 is a winner. Now you plug in pi, sine of pi plus cosine pi. Well, we get a 0, we get a -1, we get a -1. That's not what we were looking for. That's one that we have to throw out. It did not work. Okay? Same thing with the pi over 2. Plug it in. We get a 1 plus a 0. That works. But when you plug in 3 pi over 2, you get a -1 plus 0. That's a -1. That one doesn't work. So when you give your final answers, and this could drive some of you crazy on the quiz or the homework, you're getting the answers, which it looked like all 4, but you have to test them. If you were to type in 0, pi, pi over 2, and 3 pi over 2, even though you did everything right, you're going to get it wrong because the only solutions are the ones that actually make the equation true, just 0 and pi over 2. So just keep that in mind, and remember, the process is if you square a problem on both sides, okay, if you square both halves of an equation, then that may come up. Okay, now the last couple slides here are just another way to do this one. I'm not going to show it in class, but if you want to download the PowerPoint, you can look at them just to give you a better perspective of that. Another way to look at them. I like the way that I showed you. That's why I'm just going to stick with that one. It's up to you, though. If you feel you want to, go with that, by all means, don't be afraid to look at another one. If that makes more sense to you, go with that one. Both cases are going to give you the same answers, so you should be fine. Okay, so that was, again, back in our video resource area. Now to our assignments. Let's look at the 7.5 homework. It's homework number 6. You should see it. Should be the first half of the problems. Now, there's 59 problems, but this is 2 sections, so we'll probably do, let's see, we'll go up to number, looks like 27 today. So let me just do the every 4 like I tend to do here for the video lectures. Select the correct answer choice that completes the sentence below. 2 triangles are blank if lengths of 2 corresponding sides are equal and the angles between them have the same measure. Okay, see if you remember that. Should be that congruent one. So that was it. That was that side angle side thing. Okay? All right, so now let's go. That was it. Like a lot of your homeworks, as you guys see, that first question or 2 are kind of not much to them. Okay, now this one. Use a sum or difference formula to get the exact value of the trig function sine of 75 degrees. It does not matter which of the formulas you pick. We've already done this problem today, but any one of them is going to be good. I tend to just gravitate toward an addition and say, let's just go with 30 plus 45 degrees. All right. Now, based on my formula, and I'm going to put my formula right here. Remember, it's the sine of alpha cosine of beta plus cosine of alpha sine of beta. Try again. Plus cosine alpha sine of beta. Okay, that's just me writing the formula. Now, I know this formula. I've been doing this for years. You guys just learned it. But notice even though I know this formula, I'm writing it every time. There's two reasons. Number one, it helps me to memorize it, or in my case, just helps me to keep remembering it. For you guys learning it for the first time, this will help you to memorize these because they're all easy, all four of those, but it's easy to mix them up. You'll find yourself using part of the sine formula and then part of the cosine, which is 100% wrong. This helps you to memorize them. And why I like it most is it gives me room to work straight down and say, okay, this is my alpha, this is my beta. So I'm going to put sine of 30, cosine of 45, plus cosine of 30. And I'm sorry, I'm running out of room here. Sine of 45. And I was going to keep going a little more left here. Now I do my answers. Sine of 30 is a half. And what also is great about these problems, if you still have not yet memorized all those values in my table down here, you're going to get to know them pretty quick because you're going to use them. You're doing 4 of them at a time here in this problem alone. So the cosine of 30 degrees is square root of 3 over 2. Sine of 45 degrees is square root of 2 over 2. Any questions on the formula, the rewrite, the answers that I have plugged in so far? And then now we get root 2 over 4 plus root 6 over 4. Just go get your common denominator, make them into, root 6, one fraction here, and that should work. Okay, now there's a lot of steps going on, so I'm just going to give you that heads up and tell you it's easy to make mistakes. I'm not hoping for mistakes, but they unfortunately will happen because all it takes is one mistake here and one little thing to go wrong and everything's going to be off on your problem. So make sure you got that. We got that one right. Any questions on this one before I erase it from the class? Okay. Again, let me know. Don't even wait for me to finish. Start asking me a question or cut in because I want to move through these, and sometimes I may be quick on the trigger here to erase the entire screen. As I mentioned the other day, once I erase it, unfortunately, it is gone forever unless I go watch the video tonight and replay it. Okay, find the exact value of this expression, tangent of 11 pi over 12. Okay, now, like I did the other day, or not the other day, an hour ago, when I have tangent of some weird angle like this, if you want, it's not required, you can go and convert this to a degree measurement just so that you have a better understanding of where you stand on this. It looks like I have 165 degrees. Okay? I do that just because to me, it's easier to find two angles that add or subtract excuse me, into 165 versus trying to guess what adds and subtracts to be 11 pi over 12. Okay, so at least I know, hey, how about I make this 120 degrees plus 45 degrees? That'll work. Okay, and the reason I like 45 degrees, if you remember the formula for tangent, it's going to find the tangent of alpha and the tangent of beta. I know the tan of 45 is all ones. Okay, and that's the nice part of that one. The tan of 120 is going to be different, but we'll get to that one as time approaches. So we have the tangent of 11 pi over 12, which is the same as the tangent of 165 degrees, which is the same as the tangent of 120 degrees plus 45 degrees, which is the same as the tangent of 2 pi over 3 plus pi over 4. It doesn't matter. All these are going to work, but this is kind of the long way to get to that one right there. It doesn't matter because as long as you apply the formula and do it right, you're going to get this answer. Okay, so again, I told you don't have to memorize this one. I'll forget it after a couple weeks until I teach this class again because it's not a common formula. But if you're trying to test yourself, just think, okay, wait a minute. I think it's tangent of the first. In fact, I'll write the formula over. Let's go down here. Tangent of alpha plus beta. Okay. Tangent of alpha plus tangent of beta Remember, you add them on the top and on the bottom, it's 1. And the sign is the same here, but it's the opposite on the bottom. And this is the one where we do tangent of alpha times tangent of beta. So my way to test myself and you guys to test yourselves to help memorize this if you want on the homework is try to write them like that. Write this by memory. And then before you do any more work, go get your, in our case, I'll pull up our PowerPoint. Okay, I'm confident we have it right, but let's just go look at the PowerPoint anyway. What are we on? 7.5. It's around here somewhere. Then you can check it here. And the reason I say check it now is because if you got it wrong, you don't want to do all this work for nothing. All the work I'm about to do in a second, but you see how it matches right there? Tangent of alpha plus beta is tan alpha plus tan beta over 1 minus the 2 multiplied together. That way, now we know I can proceed and I can fill in the blanks. And as opposed to if I did the formula wrong, I got to redo everything. So this is going to be tangent of the first, 2 pi over 3, plus tangent of the second, pi over 4, all over 1 minus the 2 things multiplied together. Okay, so now, like I said, I can get rid of our formula since we know we have it correct. We're on the way to getting our correct answer. Any questions from any of you here while I'm erasing and getting ready for the next phase? Now the good thing is, I still have to know 2 things, but I just have to know what tangent and the tangent of each of these little angles is. I got to know the tan of 45. I got to know the tan of 120. So as I mentioned earlier, well, I know the tan of 45 is 1. So at least I can plug in the 1 for this and this. Okay, if you don't know the tangent of 120, that's not a problem. Put my cheat sheet out right here. Okay, look at 120, which is 2 pi over 3. Remember, the tangent is sine over cosine. So the 2's will cancel. If I'm dividing these two, it's basically going to be negative square root of 3. Okay, because remember, it's sine over cosine. It's square root of 3 over 2 divided by negative 1/2. The 2's cancel. The negative gives me that negative root 3 right there. So that's all it is. There's not a whole lot of extra. I now just want to try to clean this up the best I can. I'm guessing it won't matter either way. You can call it the negative root 3 plus 1, or you can say 1 minus root 3 on top. And on the bottom, you have 1 plus root 3. And don't worry, if you want to think, oh, I think I can cancel, this is good enough. You have our expression. You have an exact answer. What I don't want you guys doing is saying, hey, the 3's will cancel, the root 3's will cancel, the 1's will cancel. No, because as I said earlier today, there are 4 terms in this fraction. Look in that box. The 1, the negative root 3, the other 1, and the positive root 3. Why I want to know the terms is, if you want to cancel, you better cancel from all 4. So those root 3's, 2 of them have a root 3, but because the other 2 don't, there is no canceling that can take place here. Nothing goes away. So we leave it as it is, and this will be what I'm going to enter, hopefully for our exact value. Okay, sorry. All right, let's do it right. Got the fraction. We have a 1 minus the root 3 all over 1 plus a root 3. And there's our answer. Questions? Okay, so you notice you're not going to have as many problems here, but the problems are going to take a few more minutes. And the reason I like to do some of these problems during the lectures is I want you guys to have an awareness, an understanding, and a reality that this is not a quick homework. You better be, hopefully almost done with homework number 5, which was the 7.4 stuff. Maybe even done with a quiz, or at least take one version of the quiz. But this homework 6 is going to take a little bit of time. So, it's not difficult, but it does have a number of steps you have to do here. Okay? So number 15, question number 15. We have sine 45, cosine 45, plus cosine 45 sine 45. One way I can do it is I can just find each of these values and I can then, I can get each value, multiply them, add them up and get the answer. Or I can look at it and say, this looks just like the sine of alpha plus beta formula. Sine of alpha, cosine alpha, plus cosine alpha, sine alpha. It's the same thing. So I can say it's the same thing as me taking the sine of 45 degrees plus 45 degrees, which is the sine of 90 degrees, which is a 1. That's the fastest way to do this, even the way that you can potentially do it in your head and get the answer right. But like I said, you could take root 2 over 2, root 2 over 2. Multiply them together, and that gives you 2 over 4, which is a half. Do the same thing over here. Half plus a half is 1. Same thing. So the whole point of this one is try to see if you could do it a little faster, but at worst, you can just plug in the values and get the answers off the table like we've been doing in the last couple problems. Okay, let's look at number 19 while we're here. Okay, establish the identity. Tangent of 3 pi plus, where are we at? Theta equals tangent of theta. Okay, so there's going to be a couple steps going on here, but this is the problem we can do. And notice again, they're telling us show the steps in between. Just kind of look at your answers. Don't be afraid to jump forward and look at those answers. So our ultimate goal is tangent of theta. Well, I'm going to treat it this way. If I know when I have two things in a tangent parenthesis added or subtracted, I have formulas for that. Remember? Tangent of alpha plus tangent of beta, all over 1 minus tan alpha tan beta. So that's going to be my first approach. Rewrite this as tangent of 3 pi, plus tangent of theta, all over 1 minus tangent of 3 pi times tangent of theta. Okay, so if I kind of scroll up here and look at my answers, you kind of see the choices that we have. And that's almost the first answer for each of these. So look at my A, B, C, D choices, and you can see that there's a couple here. Look at what I have right here. Tangent of 3 pi plus tangent of alpha. That's good, that's good. This has a negative. This has a negative. So just right now, I know these two are gone. If I don't do another step in this problem, we're 50-50. Okay? I can guess, and I'm going to get a 50-50 chance of getting it right. But I want to keep going, because my ultimate goal is this tangent of theta up here on the right that I'm shooting for. Okay, so now I got to think, what's the tangent of 3 pi? Let me work this over here. Tangent of 3 pi, recall, is the same as tangent of pi. Remember in our circle, or our path here? That's 1 pi. That's 2 pi. 3 pi is right back to tangent of pi. So if I know tan of pi, I'm going to be fine. And I do know tangent of pi because it's sine of pi over cosine of pi, which is 0 over -1, which is just 0. Okay, that's going to come in beneficial because now that's a 0. I don't know anything about tan theta. 1 minus 0 there times tangent of theta. So basically, that's going to go away. That's going to go away. All I'm left with is tangent of theta over 1, which ultimately, of course, is just tangent of theta. So look at what we get here. This answer looks like it has everything that I have in that next step. This one is close, and it's unfortunate because, oh, I see. I didn't even notice this part. This was wrong in the get-go because they had a plus down here. Ultimately, it wouldn't matter because it becomes a 0, but officially, yeah, this part was wrong. My only answer is A, and there it is. So like the identities that we had to establish the last homework 2 days ago, you want to look at it as just do your identity proof. Do that thing I did on the right and then see what the multiple choice, which one best matches what the answer was. Okay, so on this one, we'll do a couple more here and then I'll let you guys go. We have cosine of theta minus k pi equals negative 1k cosine, and k is an integer. All right, now this one's going to be a little more interesting. It's not always fun, but I'll show you guys how it works. Number one, let's go and do the formula. Remember, alpha plus beta, alpha minus beta here. Okay, so that becomes cosine of the first, cosine of the second, this k pi. And then we do the opposite sign. Remember, if this is a minus, we do a plus right here. Then it's going to be sine of theta, sine of k pi. Okay, so now I'm going to look at the one part we know. K is an integer, 0, 1, 2, 3, 4, 5, even negatives. So if I start multiplying different k's, 0 pi, 1 pi, 2 pi, 3 pi, it doesn't matter what I have because sine of every one of them is 0. They're all going to be 0. So that means this whole thing is gone. I'm just left with cosine theta times cosine of k pi. Okay? So now's where it gets a little interesting here, okay? What happens is I'm trying to figure out, if I think of all the different k's, k equals 0, 1, 2, 3, 4, 5. When I plug those in to this part right here, look at what we get. When it's 0, I get cosine of 0, which is 1. When it's 1, I get cosine of pi, that's a negative 1. Here it's 2 pi, cosine of 2 pi is 1. And you see the pattern, it keeps alternating back and forth. Essentially, when k is even, you're going to get a 1. When k is odd, you're going to get a negative 1. Well, that's all you're getting. You're getting ones or negative ones right here. This is what this part is saying, okay? When k is a power of 2, 4, 6, 8, 10, it makes the negative 1 go away and you get a plain cosine. When cosine is odd, then you get a negative cosine in front of there. So it's kind of one of these where you have to just play with numbers and see what you get, but it's a hard one to establish as a proof, okay? My way to do it is I would just go, let's make two different lines. Here's going to be when k is even. Here's going to be when k is odd to prove it. Now let's look at what they actually did though, what our choices are, and see if we can find the one that closest represents what we had. So start with this first part. Okay, this is the splitting of the cosine right here. Notice it's a negative, so you have to have a positive, the opposite sign inside. That means B and D cannot happen. Everything else is identical in that green box. They're all, not all. They're supposed to be cosine, cosine, sine, sine. These have cosine, cosine, sine, sine. This one doesn't, and it did have a positive, but it's gone because it didn't have the right stuff right there. Okay? So far that's good, and that's good. Now we go on to the next phase, and you see, again, we're not looking at this. This is eliminated, this is eliminated. Look at what they have here next. You have a cosine theta and a cosine theta. We had that. Okay? Now this is the weird part. We'll get to that in a second. But over here is where I want to focus on is it's a sine theta and a sine theta, but we already talked about it is no matter what the k is, that's always going to be a 0, just like this. It's never going to be a negative 1. That's all I need to say, okay, it's got to be C. There's my answer right there. I sort of just process of elimination. I knocked out this one and this one and this one, and I'm left with just one possible answer. Okay? Any questions, anything on that one that you're not sure of? Okay. Okay, so let's look at next problem. All right, number 27. Okay, so now we get one of these combo problems. Let me give myself some more room here. We have the exact value, so no calculator, and you can't really plug this in anyway, but we want to get the tangent of the inverse sine of 3/5 minus the inverse cosine of 1. So remember the process. I'm going to let that be my alpha, that be my beta right here. That's what I'm going to work on first. So sine of alpha equals 3/5 and cosine beta equals 1, all based on what was presented right here. I'm not dealing with the negative out front. That's going to go in the second half of this problem. Okay, so we make triangles for each. Here's my alpha triangle. Sine is going to be y over that. And if you do the Pythagorean theorem, remember I told you 3, 4, 5 triangles, or you can go and just do the Pythagorean theorem and you'll find the x has to be 4 in this case. Over on the beta triangle, treat this like 1 over 1. And this is going to get interesting because it's like, wait a minute, if that's a 1, sorry, not that one. This is a 1, this is a 1. How am I going to get, sorry, one more time. The 1's down here on the bottom, x. X is 1. The y is my mystery. So some of you may already be looking going, how in the world are we going to do this? You'll see. Still, use your Pythagorean theorem. Y squared plus 1 equals 1. Y squared equals 0. Y equals 0. That is your value right there. Remember, you can get zeros. We have that every 90 degrees. Somebody is 0. Half of them are zeros. So let's see how that plays into what we have here. So the formula says we're looking for tangent of alpha minus beta. That was back up here, what we're trying to find. We have an alpha triangle. We have a beta triangle. Therefore, we should know everything about each of those triangles, including the tangents. So the formula is tangent of alpha minus tangent of beta all over 1 plus tan alpha tan beta. I'm going to move side. Let's move over. Let's move down. I got a little bit of room. So from the first triangle, the tangent is going to be 3 over 4. Here, the tangent is 0 over 1, so it's just a 0. Then we have 1 plus 3/4 times 0. Clean that up a little bit. We have a 3/4 on top. We have a 1 on the bottom. Should be all nice and neat down to a 3/4. I did that kind of quick, so I hope I didn't miss anything. You guys see anything wrong with it? All right, we got lucky. We're good. 3/4. Any questions on this example? And like I said, this is a standard procedure. Every one of the problems you see in a homework or quiz like this, where you have a trig function and you have a plus minus of a couple inverses, call the first one alpha, call the second one beta. You must make 2 separate triangles, 2 separate Pythagorean theorems, then go apply the new formula of whether it's sine, cosine, or tangent of the alpha plus beta, alpha minus beta, and then fill in the 4 trig values, whatever they may be, based on the triangles, and then simplify, and you have your answer. So again, it's a problem that I love to give in a class test or a quiz because it just shows me a little taste of everything. It's like a number of steps from pretty much everything we've learned this semester. Okay, so let's get rid of this. Let's go on to number 31. Okay, yeah, I did take out 30. I took out a few of these because the stuff they had really wasn't going to help you guys. So treat the last few problems out of 7.5 like freebies. Then we get to 7.6. So I'll stop there with the homework. my last thing, let me just talk. I'm gonna start to talk about 7-6 just to get the ball rolling for you. And you're gonna find here on this one, let me just talk for the last 10, 15 minutes of just what this is, and then we'll pretty much spend Friday going over the rest of this 7.6 stuff, and then I'll do the rest of the homework, and then we'll talk quiz it from there. So 7.6, we have our double angle and our half angle formulas. Basically, it's just another set of formulas to change some things where you have. So here's the ones that you're going to use the most. If you have sine of 2 theta or cosine of 2 theta, you have some rewrites. Now, what I want to show you here is how in the world they got these. I'm going to give you a little bit of a background. If you want to get sine of 2 theta, well, remember, what does 2 theta mean? It simply means theta plus theta. And based on the section that we just finished, we know this is the same as sine of the first cosine of the second. Oh, sorry. Yeah, plus cosine of the first sine of the second. Well, it so happens because they're the same angle, this is essentially sine, cosine, and another sine, cosine, because they're the same angles. And that becomes 2 of them. So that's how they got this one right here. For the cosine, it's the same thing. When you get cosine of 2 theta, it's cosine of alpha plus alpha. Sorry, theta plus theta. And then that gives us cosine of theta, cosine theta, minus sine theta. And that's why we get cosine square minus sine square for that one. That's how they get this formula. And just so you know how they got the other two, they took that and replaced it with a 1 minus sine theta, square theta from your Pythagorean identity. Combined these two and it became 2 of them. And of course, you can do the same thing by replacing this with 1 minus cosine square theta to get that one. So all 3 of these, of course, they all come from cosine 2 theta. They're all the same. It's just a matter of preference, and sometimes one is going to be more advantageous or one of them is going to be really directly related to whatever the problem was of the day. Okay, so you're going to get a couple of examples how to do this here. If they give you a theta and you want to find out what the double of it is, you can't just double this number, by the way. There's a process, and we have our formula, 2 sine cosine. So the first step, even though it looks like it's going to be quick, and again, let me show you where we're at here. This is all they give us. Sorry, this right here. They tell you this, one more time. They tell you this first part. Just from that, and you want to find this, a lot of people look and say, well, I should just be able to go 10 12ths or, 10 over 6, something. They think you can just double. It's not that simple. You must build the triangle. They tell you where it is. So it's over here. Let me erase and start over here. Sorry. Make this a little bit neater for you guys. Apologies. So in this case, even though you have a formula, there's still a procedure. Okay, because think about it. The formula was, remember that? Cosine square minus sine square? Oh, go back. Keep referring back to our formulas here. Remember that one? Oh, sorry, where were we at? We're at sine. I'm on the wrong one. 2 sine cosine. Either way, you have to know both of these, okay? So the formula is 2 sine theta, cosine theta. We're doing sine 2 theta. So we didn't know both of these. All we know is sine right now. So at least I can say that's going to be 5/6, but I don't know cosine. How am I going to get cosine? I'm going to make my triangle. So they tell us that your theta has to be between pi over 2 and pi. So it's in here somewhere. I know it's 5/6, so that's a 5, that's a 6, and I have to do my Pythagorean theorem. X squared plus 25 equals 36. X squared equals 11, so I need plus or minus root 11. And look at where you're located. This is going to the left. It's second quadrant. Your cosine must be negative. It's negative root 11 over 6. So when all is said and done, I multiply these together. Remember, we're not adding, so you have to get a new denominator of 36. So I have negative 10 root 11 over 36, and if possible, reduce this down. Negative 5 root 11 over 18. Okay? That's the step-by-step process that you have to do to do this. So they use the unit circle still. I like the triangle. So either one is going to work here when you do this. And just kind of eyeballing it to make sure we're getting the same ones. There's your root 11. It's a negative root 11 over 6. And now they plug into the formula, just like I have right here on the bottom left. And hopefully there's my negative 5 root 11 over 18. Okay? So there's your step-by-step on how to do this. So there's not a whole lot. This section is a little bit more complicated because the formulas are not as nice and neat as the sum and difference ones we just did in 7.5. But once you have the formulas, you can simply go and figure out what the answer is. It's just a matter of doing the plug-in, doing the triangles, and getting all your answers. So in the second half of this, you want to find cosine of 2 theta. Well, the formula is 1 minus 2 sine square. And what's nice about this one is if this is all they asked you, it's great because they gave us sine in the beginning. You can actually do, so let's scroll back a little bit. Remember what was given on this problem. They gave you the sine and they told you where it was. So to get this answer, I needed to know sine and cosine. But for the cosine of 2 theta, remember that formula? We have 3 formulas. One of them only needed sine. So that was what they're doing on this one. This cosine of 2 theta, we have a formula, okay, that says it is equivalent to, 1 minus 2 sine square theta, regular theta, which is what we have right here. So to clarify, it means this here. And since we know it's 5/6, I can simply plug in the 5/6 here, square it, multiply it by 2, and that's how they got the answer that they had. Saves you a lot of trouble there. And I'll just go right to the end. Okay, where is it? Here's the cosine. They plugged it in. They get that 1 minus 2, 25 over 36, 1 minus 25 over 18, negative 7/18. That's our answer. Much quicker. You didn't need the triangle. So it depends. Most problems you're going to need the triangle. Every now and then you get to kind of luck out and you don't have to worry about that. Okay, so these other ones, we're going to make some identities. They want to come up with a formula for tangent of 2 theta. They want to come up with a formula for sine of 3 theta. Now, in practical purposes, you probably aren't going to have to know either of these, especially sine of 3 theta. Very rare. And cosine of 3 theta, not going to come up much, but it's an exercise to kind of get you to use what you know and to connect the dots and to move to the next level on these. All right, so where are we here? Just want to make sure we don't run out of time. So we'll work a couple minutes and then I'll call it for the day. We have tangent of alpha plus beta. We know that one, okay? This time though, they're both, because we want to make a 2 theta, they're both going to be alphas. So plug it into our formula. It's going to be tan of theta plus tan of theta minus 1, divided by 1 minus tan theta. All right, that becomes 2 tan theta over 1 minus tangent square. And that was it. That's all they wanted. That is the new formula. There's no more to that one. Okay, the sine of 3 theta, they wanted you to make everything as sines and cosines. So in this case, we're going to rewrite 3 theta as a 2 theta plus a theta. And we have formulas for both once we break it down. So we're going to use the sum formula from the last section, the one earlier today. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. And then now we use that double angle formula, the one we just learned. So we replace this one with 2 sine cosine. We replace this one with cosine square minus sine square. And then we just try to clean it up a little bit. And there's a little cleaning up we can do. I know we can factor out a sine. Oh yeah, I'm sorry. These right here, these are identical, so we can just make 3 of them. And if you want, you could factor out a sine and just leave it as they did right there. So, like I said, it's just some exercises to get you going on these. Look through these a little more in depth if you want. And I'm going to pick up with these. Let me pick up with this slide right here. I'll go with these formulas. But they're just, again, replacements so that what you're going to be doing, you're going to be going back and forth. There are going to be times where you have a sine square, and you're definitely going to get that soon, and you want to rewrite it this way. Now, some are going to say, why would I want to do that? There's going to be reasons of, I'm having trouble solving it with this square. I can't do anything. This square is messing me up. I'm going to solve it easier if I can get it down to a single power. Okay? Then there's going to be also times where, when we're doing identities or other things later, we're stuck. I don't like this 2 theta. I can move it this way. So just keep in mind, every formula, every identity that you get, it works both ways. It works both directions. It's not one or the, one way every time. You literally will be using these both ways. Okay? So I'll stop right there. I'll pick up with these formulas next time, and then I'll show these examples and do the rest of these. So on Friday, we'll do this. We'll finish the slides for 7-6. I'll finish the homework for homework number 6. I'll finish the rest of those problems. And then in the last few minutes, we'll go over some quiz problems, just kind of give you a quick preview of what's going on. In the last minute or two, let me see if I can do this. Just for those of you who are ready to do quiz number 5, let me just give you a quick look at